Greetings. Welcome to today's session on anti-lock brake system and vehicle stability. So, alright. Greetings. So, welcome to session on anti-lock brake system. So, this is portion of the lab module which we generally run in our course, and part of it has been uh, brought in here so that we can have a discussion on that. So, in previous sessions, we have discussed. In the previous session, we have discussed about things like foundation rates and all. Okay, so today we'll be discussing about critical active safety system called anti-lock brake system. Right. So let's get started. This will be the outline of today's work. So first we will be starting with some introduction. We'll have discussion on commercial solutions and we'll have some discussion on our research, and then we will connect things on where we are. So, looking at the introduction, let's see why, what and how for anti-lock brake system. An anti-lock brake system is a system. Uh, what is it? It is active vehicle safety system that prevents wheels from locking and it assists in retaining the vehicle control. Why do we need anti-lock brake system? We need it because wheel lock can destabilize the vehicle, and in the case that if front wheels lock, it would result in loss of steerability of the vehicle. That means the steering input given by the driver, in case of if the front wheels have locked, will not result in any kind of lateral motion. Similarly, if rear wheels lock, so okay, so rear wheel lock can result in lane departure. That is, it can have some kind of unintended yaw motion. So if the vehicle is moving and rear wheels have locked, even small perturbation in lateral direction can result in undesired yaw motion, and you have a chance that your vehicle can hit the vehicle in neighboring lane. Okay, so to prevent wheels from locking, we have anti-lock brake system. So how does this anti-lock brake system work? It works on regulation of it works on principle of regulation of wheel slip ratio. Okay, so if you were to draw a very simple control block diagram where we have the vehicle and we have slip and its reference value to be given as control input. Okay, so if we know where to regulate wheel slip ratio and what is wheel slip ratio for each wheel, we should be able to control the wheel slip and prevent wheels from locking. So, in essence, an anti-lock brake system, or ABS, is a vehicle safety system that regulates wheel slip ratio to prevent wheel lock. Let's see what wheel slip ratio is. Okay, the wheel slip ratio is defined as R omega minus V by V. Okay, right. So the wheel slip ratio is defined as R omega minus V by V. Just 1 second, some issue with my recording. Alright, so okay, we are good. Yes. So the wheel slip ratio is defined as R omega minus V by V, where R is the vehicle's R is the effective tire radius, V of T is vehicle's longitudinal speed, and omega is the wheel angular speed. So the wheel slip ratio is related to the tire road friction coefficient as shown here in the mu lambda curve. Let me highlight it. So, so there is in this plot I have shown the mu lambda curve for two different kind of surfaces, one for a low friction surface and one for high friction surface. So this mu lambda curve has two regions divided by the peak, right, lambda peak. On one side it is stable and on the other side it is unstable region as indicated in this figure. So what happens in the unstable region is that wheels rapidly go to lock and it cannot be recovered from lock unless otherwise there is some kind of control intervention. So we would like to satisfy two objectives in this case. We would like to regulate our wheel slip ratio as close to the peak as possible, because then we will be able to utilize the tire road interface to its best capacity. And secondly, when we have on the second thing is that we would also like to keep prevent our wheels from locking and keep it in the stable region. So we would like to operate in this desired operating region, which is on the stable side, yet it is closer to the peak. So in this case, I have shaded these two desired operating regions. So now let's move on and let's have small discussion about wheel lock and friction ellipse. So in the classroom, we had discussed friction ellipse, where we plot the longitudinal force Fx and Fy, that is the lateral force. So each tire road interface is limited by its capacity to generate force at the tire road interface. So that capacity is denoted. That capacity is denoted by ellipse, by this boundary of this ellipse. Alright. So any force which is being demanded by the vehicle inside this friction ellipse will be satisfied. However, if the demanded force is larger than this, then we would end up getting a force which is inside this ellipse, and it is also it would also correspond to wheel lock. Okay, so in a sense, the friction ellipse denotes the maximum possible force which can be provided by the tire road interface, and if the force due to braking torque is higher than that what the tire road interface can provide, then wheels lock. So by this statement, what we mean is that when we apply the brakes, the wheels, the brake torque gets generated. That brake torque, if its corresponding force at the tire road interface is smaller than what the tire road interface can safely sustain, then we can be positive that there will not be any wheel lock. But if in case the corresponding force, the force corresponding to the brake torque is higher than what tire road interface can sustain, we are going to look at wheel lock. So our ideal ABS operation is at this point, where we get maximum amount of braking force in the longitudinal direction but that also means we are going to get zero amount of lateral force whatsoever. In reality, in many of the cases, we will never know what that ellipse is, and our operating point will slightly be inside this ellipse, which essentially results in uh, suboptimal utilization of the tire body interface. However, that is a practical trade-off. So let's take a look at commercial solutions. We have borrowed this material from this source called ABS6 Standard Anti-Lock Brake System. It's a product manual from Knorr-Bremse, published in Munich, Germany in 2009. So this is this resource is available on the web and you can take a look at it for more details. Let us take a look at this schematic and understand various components in the ABS system. So looking at this, we have a 4S4M configuration. A 4S4M configuration means that the ABS will have 4 wheel speed sensors and 4 modulators. Modulators are the devices which would take an electronic signal coming from the electronic control unit or the ECU, and it modulates the brake chamber pressure, which would result in modulation of braking force and braking torque. Okay, so there are 3 key components as shown here. First is the wheel speed sensor, second is the modulator valve, and third is the electronic control unit. So during normal operation, when the driver presses the brake pedal, the signals pass through as usual. But if in case wheel lock is detected, the ECU's signal overrides that of the driver and brake chamber is modulated. So the output of these wheel speed sensors is indicative of wheel speed, and the modulator valve essentially modifies the brake chamber pressure to regulate wheel slip ratio. So this is one schematic of the modulator valve. Okay, and you can see that inside the drum brake there is a ring with teeth, or you can or an encoder. Industry standard term is pole wheel. So this pole wheel has few metallic teeth which rotates in front of this wheel speed sensor that generates a sinusoidal signal. So this sinusoidal signal is indicative of wheel speed, which is read by the ECU, and it appropriately determines the 3 phases of valve operation. So at point 1 here, the air comes in. At point 2, the air goes into the brake chamber, and at this particular point, you can exhaust the air from the brake chamber. So you can see that there are 2 solenoids here, denoted here as C and D. These 2 solenoids, these 2 solenoid valves are either off, or can be kept on or can be kept off, denoted here as 0 and 1. So if we were to consider 3 phases of operation, that is apply, hold and exhaust. In apply phase, we want to increase the brake chamber pressure. In hold phase, we want to keep the brake chamber pressure exactly the same. And in exhaust phase, we want it to be brought down to the atmospheric pressure. So if we open the apply solenoid and close the exhaust solenoid, the air would flow from the reservoir to the brake chamber. In the hold phase, when both the solenoids are closed, no air comes in and no air goes out, essentially resulting in a hold phase. And finally, when the brake torques are too much and wheel is trending towards lock, so yes, when the wheel is trending towards lock, we would like to exhaust some brake chamber pressure let some air come out so that the brake torque reduces and the wheel starts spinning again, uh, avoiding wheel lock. Now looking at the wheel speed sensor, uh, in this figure you can see that there is this sensing wheel which looks like an encoder, and there is this wheel speed sensor which has a coil and a magnet. As this sensor ring moves in front of it, because of the presence and absence of teeth, a sinusoidal signal is generated. Yeah, a sinusoidal signal is generated. Now, this sinusoidal signal needs to be processed even before we can call it as wheel speed. So, if you can see here, this is the sinusoidal signal, and we use something called counter in an electronic control unit or ECU, which can count from 0 up to certain finite value, and then it resets. So if we were to measure the frequency of this particular sine wave, we can do this by counting the time taken from this one particular zero crossing to this zero crossing, using this kind of algorithm. Every time a rising edge is detected, we reset yk to be -1, and then uh, every time the counter resets, we would set it to 0 and 1 and so on, right? Till the time we detect another rising edge. So we can keep a count of how many time steps have passed with respect to the clock of microcontroller uh, to figure out the value of time taken by one period of sine wave. And then we can plug that number as n, use number of teeth and the sampling frequency of the microcontroller to finally obtain wheel speed or omega. Right, so this is how we measure wheel speed. Now let's come to wheel slip regulation. As we saw in the mu lambda curve, we would like to keep it in the stable region and we would like to keep it as close to peak as possible. So in this particular illustration, there are various things as shown here. First is the vehicle velocity with dotted blue line. Second is something called reference speed, which is calculated by the ECU. And third is wheel speed signal. Fourth is pressure in the service brake actuator, and finally, fifth is the modulator state. We can use apply or build interchangeably. Hold and exhaust are essentially the same phases. So once we start applying the brake, what happens is that the wheel slip starts increasing and there is a rapid change in the wheel speed due to deceleration. Right. So as we start braking and increasing the pressure in the brake chamber. If there is a lot of change in, if there is rapid deceleration, the rapid deceleration can be indicative of impending wheel lock. That is, we might expect wheel lock if my deceleration is too high. In such a case, we would trigger an exhaust phase to release some brake chamber pressure and help the wheel accelerate. So around this point in wheel speed, the pressure started exhausting and we can see that it takes some effect and you can see that it's curving upwards, indicative of acceleration, right? So here you can see that the wheel speed is increasing. As we see that the wheel speed is increasing, then we can essentially stop the pressure release and hold it. So now what we are doing is we are holding the brake chamber pressure constant. That would result in some braking. So every time this happens, we are doing some incremental pressure in steps. And around this point, there is some kind of recalculation of reference speed. Okay. So the big question in this problem is, how is this reference slip calculated by the ECU or electronic control unit. Now let's move on to the portion of our research where we try to address how this is done. So this is again the simple block diagram which we discussed in the beginning, where we have a wheel slip controller for the vehicle. We take feedback of wheel slip ratio and we take the lambda ref. But when we want to regulate the wheel slip ratio, there are two big things. First is we want to identify the reference slip. We do not know what kind of new lambda curve we are dealing with. We do not know what kind of road surface we are on. So, if the vehicle does not know what kind of road it is on, how will it find the value of reference slip? And wheel slip ratio cannot be directly measured. So, it needs some kind of estimation. So, we are asking how do we measure wheel speed, how do we estimate the effective tire radius, and how do we measure the acceleration. So we have sensors for measurement of wheel speed and acceleration, but effective tire radius is something which changes with inflation pressure, it changes with the loading conditions and all, and it needs to be estimated in real time for the application. So these are the big challenges in wheel slip regulation, and some of which we are trying to address in our research. So to highlight challenges, first is identify reference slip. Wheel slip is unknown and it varies during the operation. Second is measurement of wheel speed. As we discussed, the output of a wheel speed uh, sensor, which is of a variable reluctance type, it outputs a sinusoidal signal and it requires certain processing in hardware and software before giving it out as a value of wheel speed. Second is wheel slip estimates may drift due to inaccurate values of effective tire radius, which is one of our research which got recently published and published last year. So, where we discussed the drift in estimates problem uh, in quite detail. And as I said, uh, the inertial measurement unit or IMU, which can help us measure acceleration, its data is affected by mounting errors, pitch motion of the vehicle, and so on. And these things can have impact on wheel slip estimation. So, our question we are trying to answer is how to develop the estimation and sensor signal processing algorithms for ABS on heavy commercial road vehicles. So, these are the broad research questions we have been looking at in categorized into three categories. First is algorithm, second is implementation, and third is generalizability. So, what are practical challenges in realization of such kind of algorithm? That is where the core questions are: what is the reference slip, and how to estimate the wheel slip ratio in real time. Second is how to process the wheel speed sensor data and how do we optimize it so that we can run it on a real time ECU or electronic control unit. And finally, we are asking how to develop processes so that we can easily tune this ABS for different vehicles and how can we rapidly analyze the data. So these are the aspects we are actively working on as of today. And these are answers to some of these questions. So our research on optimal reference slip algorithm and our research on radius searching recursive least squares algorithm essentially answers these 2 points. So this is a block diagram which shows various aspects of our ABS. We have these sensors as brake chamber pressure measurement. We have sensor for measuring wheel speed. We have sensor for measuring inertial measurement unit, or we have for measurement of vehicle acceleration, and we have a brake pedal. We have processing algorithms for these things and slip estimation algorithms, reference slip identification algorithm, and wheel slip regulation algorithm. So all this with some brake controller and actuator processing algorithm which closes the loop for ABS. So this is something which we published as SWATA, or slip and wheel acceleration threshold algorithm, where we take value of desired value of slip ratio or lambda f, break it down into two different thresholds, and take it into the phase identification block, which essentially tells whether we should apply, hold, or exhaust the pressure. That is converted into a number or a value of desired brake chamber pressure using this phase to pressure mapping, which essentially increases or decreases or keeps the pressure constant. That the value will also depend on something called EPR gain, which is again a function of lambda desired. It's just a linear mapping. So that if we are looking at a low friction surface, we should be able to cap up the maximum brake chamber pressure, and it would help in uh, improving the performance. And of course, we need brake chamber pressure because of hold phase. So to identify phase, we have these uh, mapping between lambda, that is the wheel slip ratio, the two thresholds, lambda 1 and lambda 2, and we have two thresholds on alpha, a lower bound and a upper bound. So we say that if anything below a value of alpha lower bound would result into an exhaust phase. Anything above uh, below lambda 1 and above alpha upper bound would lead to apply phase, where we increase the brake chamber pressure. And in between, uh, after lambda 2 towards minus infinity, towards minus 1 rather, we have exhaust phase. That is, we have crossed second threshold and we must exhaust now, so to prevent wheel lock. And then there is apply phase if my slip ratio is between these two but my wheel is accelerating rapidly, hold phase if my wheel is accelerating slowly, and exhaust phase if my uh, wheel is already decelerating, because this happens to be slightly critical. So this is where this is how we identify the phase. So this is a brief overview of our anti-lock brake system, uh, and I think now we can move on for other things. But if you have any questions uh, on this, we can have a discussion. All right, so if there are no questions, I would like to run some problems on brakes. We'll get started with it. So these are the things which we discussed in the previous. So we'll be solving these exercise questions now. Uh, okay. So this is our first question. A passenger car weighing 12 kilonewton has a wheelbase of 3.2 meters. The center of gravity is 1.2 meter and is behind the front axle, uh, and zero point 0.5 above zero point 0.5 meters above the ground level. The brake force distribution on the front and rear wheel is 60% and 40% respectively. The coefficient of rolling resistance is 0.01. We have been asked to find out which pair of tires will lock on road surface with a peak friction coefficient of 0.8 and 0.2. Calculate the corresponding braking efficiency and provide your observations. Next, calculate the ideal brake force distribution for surface with peak friction coefficient of 0.8. And then we have to repeat the above steps for point 2 as well and provide the observation. So let's start. So we are looking at the brakes portion. Given W is 12,000 Newton, wheelbase is 3.2 meter, CG location from the front wheel is 1.2 meters. That means L2 is capital L minus L1 is 2 meters. Then we have height of CG given as 0.5 meters and FR is 0.01. So given brake force distribution is like this. KBF is 0.6 and KBR is 0.4. So from what we saw in classroom, A by G for the front wheel is given by mu into L2 plus KBF into FR into L and A by G for the rear wheel is given by mu into L1 plus 1 minus KBF into FR into L over and we have eta B as minimum of A by G into F, A by G into A by G of R, sorry, yeah, into U plus FR. So let us, using these formulas, we can calculate for mu of 0.8 and 0.2. What will be the value of A by G in front wheels, A by G in rear wheels, and eta B. So if we were to use these two equations for zero point 0.8, we'll get A by G for front wheel as 1.065, A by G for R as 0.579, and the efficiency would come out to be 71.5%. For zero point 0.2, this would come out to be 0.23. So here we can see that in both the cases, rear wheels would tend to lock first. Okay. Now let's take a look at the ideal brake force distribution. It is given by this formula KBF over KBR. For mu equals to 0.8, this KBF ideal or KBR ideal would come out to be 3.025. Since KBF plus KBR is 1, we can use these two expressions to figure out KBFI and KBRI, which comes out to be 0.75 and 0.25. So ideal brake force distribution for point 8 in this case would be 0.75 and 0.25. Now let us repeat these calculations with this ideal brake force distribution. Okay. So here, let's do this. Okay, for 0.8 as well as for 0.2. So we have these two efficiencies. So we can see that the braking efficiency by changing the brake force distribution have substantially increased from what it was previously. So now we can observe that using the ideal brake force distribution, for mu equals to 0.8 ensures that both front wheels and rear wheels tends to lock at nearly the same value of a by g. So you can see here that 0.812 and 0.807 are similar values. Further, this value of a by g is the maximum that can be obtained on this surface on the pointed surface, uh, leading to a 100% efficiency. Nearly 100% efficiency. Now let's take a look at second problem. Here we are asking to consider a single unit four-wheel vehicle having weight of 107800 Newton and a wheelbase of 4.2 meter. The center of gravity is located at distance of 2.7 meter behind the front wheel center and height of 1 meter from the ground. We have to consider a rolling resistance coefficient of 0.006 and front and rear brake force distribution of 40 and 40 to 60. Determine as to which wheels would lock first on a road surface with P coefficient 0.8. For the same vehicle, calculate the brake force distribution which would ensure that all four wheels would lock simultaneously on the same road surface. Okay, so let's get started with this. We have been given W as 107800 Newton, wheelbase of 4.2 meters, location of CG from front axle is L1, which is 2.7 meters. That means L2, which is L minus L1, would be 1.5 meters. Height is 1 meter and rolling distance is 0.006. And we are considering mu of 0.8. We have been given kbf as 0.4 and kbr as 0.6. So we will have to calculate a by g for front, which is given by mu into L2 plus KBF into FR into capital L. This comes out to be 1.375, and A by G for here is mu into L1. This value comes out to be 0.655. So looking at this, for this brake force distribution, the rear wheels would lock first. Now both front and rear wheels would lock simultaneously when the A by G ratio for front wheel would also equal to that of rear wheels. This implies mu into L2 plus KBF into FR into capital L over KBF into L minus mu into H equals mu into L1 plus 1 minus KBF into FR into capital L. Okay, so if we were to cross multiply this, we will get mu into L2 in bracket 1 minus KBF capital L plus mu square L2H plus KBF in bracket 1 minus KBF FR into capital L plus mu into minus mu square into L1 H plus these two terms will get cancelled out. This implies that it would simplify to L2 into capital L minus L2 into KBF into L plus mu into L2 into H. This will also get cancelled, and it would further simplify to L2 into capital L plus mu into L into H plus FR into L into H equals to KBF into capital L square. This implies KBF would be so. This will be the value of KBF and KBR. So if you were to take this value of KBF and KBR and then check for A by G value for front, it will come out to be 0.806, and A by G value for rear would also come out to be 0.806. This means both front and rear wheels would lock simultaneously. Alright. Now let's look at another exercise problem. So here we are considering a vehicle having mass of 1000 kg, which is traveling at initial speed of 100 kilometers per hour. Let the driver reaction time TD be 1 second. That is, the driver takes 1 second to react in applying brakes. The brake response time TB is 0.25 seconds, and the deceleration rise time TR is 0.3 seconds. So let's look at the figure. TD is the driver reaction time, TB is the brake reaction time, and TR is the rise time. So we have been asked to obtain an expression for stopping distance in terms of VI and parameters as indicated in this figure, that is A, TD, TB and TR. Then we want to determine the stopping distance of the vehicle if the final constant deceleration of the vehicle is 0.6 is 6 meter per second square. In second part, we want to determine the brake force neglecting the other retarding forces that needs to be applied if vehicle has to be stopped within 90 meters distance from the same initial speed. And later we want to compare this approach with one discussed before. What additional information would be required? So let us start. So we have TD, driver reaction time, TB, brake reaction time, deceleration rise time, Okay. The distance traveled by the vehicle during the driver reaction time and the brake response time is Vi, that is the initial speed, into Td plus Tb. Okay. And then during deceleration rise phase, so we are assuming it to be a linear model, right? So we have T divided by Tr into A bar. Then instantaneous velocity v of t would be Vi minus integral of A of t dt, which is Vi minus integral of T divided by Tr into A bar dt divided by 2Tr. So the distance traveled by the vehicle in this phase is given by integral 0 to t or v of t dt. So this will become Vi into Tr minus A bar Tr square by 6. Now in the stopping phase, the initial speed at maximum deceleration is and time required for stopping is Ts. So the corresponding distance traveled here would be ds minus a bar ts square by 2. After substituting value of ts from above, it simplifies to bi minus a bar by 2 to tr whole square by 2a bar. Thus, the net stopping distance would be so the net stopping distance would be bi into td plus tb plus a bar. This finally simplifies to so for the given values of td 1 second and tb to be 0.25 seconds, er to be 0.3 seconds, vi was 100 kilometers per second per hour, that means 27.78 meter per second, and the value of a bar given was 6 meter per second square. Stopping distance would become 103.17 meters. Now in the second part, you want to stop the vehicle in 90 meters. So if we were to simplify these numbers, you will get a quadratic equation in a bar So we would require a bar of 7.55 meter per second square to brake the vehicle in 90 meters. And corresponding braking force would be F equals to M into A bar, which would turn out to be 7.50 Newton. Alright, so in today's discussion, to summarize, first we took a look at anti-lock brake system and we understood how anti-lock brake system works. And then we solved three problems related to braking and stopping distance, brake force distribution, and tendency of wheel lock. So that's all I have for today's discussion. If we have any further questions, we can wait for a couple of minutes or we will close the session. So yeah, we are closing the session, but if you have any questions, we can take them up. Alright, if do you have any questions? Alright, there are no further questions. Let's close today's session. Stopping to record.